about refraction today. So we've already talked about reflection, looked at reflection with mirrors, and now we're going to look at refraction, which is the part of the rays that go through the medium to the other medium. So refraction involves the portion of the wave that travels into the new medium. Travels into the new medium. When light travels in air or a vacuum, its speed is 3 times 10 to the 8th meters per second. Remember, that's the speed of light. We use the letter C to sort of symbolize the speed of light at 3 times 10 to the 8th meters per second. When light enters a different medium, the frequency stays the same. The frequency does not change, but the velocity does. The velocity changes. Because the velocity changes, the direction that it is traveling also changes. So this causes the direction of travel to change. Okay, so in order for us to figure out how the direction changes, we have to first look at the index of refraction. But before we do that, you're going to be seeing some diagrams that all look similar, but I'll explain to you what you're looking at. So we draw a boundary here to describe the boundary between the two different mediums. So let's pretend we have air and water here. Okay, and then remember we talked about this imaginary vertical line that's perpendicular to the boundary. That's where the light will bend. So here comes the incoming ray. We call it the incident ray. So this is the incident ray. Okay, the incident ray will come in at a particular angle. The angle to this vertical is called the incident angle, theta I. Theta I. And then when it hits the water boundary or some other boundary, the light will bend. Sometimes it will bend towards the vertical, and sometimes it will bend away, depending on the index of refraction, which we're going to talk about next. And so this will be the refracted angle theta r. Okay, because this is known as the refracted ray. Okay, so the index of refraction then is the indicator of optical density. Indicator of optical density of a particular material. The way we calculate the index of refraction is we use the letter n to represent the index of refraction, and we say that n equals c over v. C over v, where c is the speed of light in a vacuum, and v is the speed of light in that medium, in the new medium. So there are two values that you should just kind of know off the top of your head, and as you do these practice problems, you'll learn that you won't ever forget them. And the two values are the n for air is always equal to 1. And this n is unitless because you've got meters per second here and meters per second here, which cancel. So the n for air is 1, and the n for water is 1.33. So those two numbers will assume that you know, and sometimes you'll be given them and sometimes you won't be given these. Any other material, you'll be given the index of refraction for those materials. All right, so that is refraction. Now, we can look at and calculate the angle that the refracted ray enters by knowing the index of refraction and knowing the angle at which the ray comes in. So we can do that by applying Snell's law. So Snell's law describes the relationship between angle of indices, angle of incidence. Described as the angle of incidence, that's the incoming angle, and angle of refraction. And the speed of the wave as it travels through the mediums. Okay, so Snell's law says N1 sine theta 1 is equal to N2 sine theta 2. That's Snell's law. Now, if the second medium is more optically dense, the refracted ray bends toward the normal. And the normal is that vertical imaginary line. If the second medium is less optically dense, the refracted ray bends away from the normal. Okay, so going back to this picture, I'll draw it down here for you. There's the boundary between the two mediums, medium 1 and medium 2. Okay. Here's the normal. That's that vertical line. That's called the normal. Here's the incident ray. Okay. Comes in at this incident angle. And if this medium is more optically dense, if its n is bigger, then it will bend towards the normal, like this. If n is smaller, so in this picture, n2 is greater than n1. If n2 is smaller than n1, then what you have is, there's your normal, there's the incoming ray, now it bends away from the normal, so you get this very large angle here. Okay? So that's what these two statements mean. theta 1 and theta 2. Theta 1 and theta 2. All right, so this is N1, N2, the optical density of these two mediums, N1 and N2. Okay, let's try out this Snell's law equation. We're going to do one problem. And let me move my boards over here. So here we have a problem that reads, a ray of light in air is approaching the boundary with water at an angle of 52 degrees. So here's your water-air boundary. Here's the normal. Here's the ray that comes in. It's a 52 degrees. It's always going to be to the normal. Determine the angle of refraction of the light ray. So the question is, what is this angle? So we're going to go ahead and use Snell's law, which says N1 sine theta 1 equals N2 sine theta 2. Plugging my values, N1 is air. I know that the optical density of air, or N of air, is 1. The angle at which it comes in from the air is 52 degrees equals water's N is 1.33, and I'm trying to find theta 2. Now when you do this math, you're going to get sine theta 2 equals sine 52 over 1.33, and then you have to inverse sine this, right? Take the inverse sine of this to actually find theta. So go ahead and pause the video here, do that on your calculators. Okay, hopefully you got 36.38 degrees. That is the angle at which it goes through the water. So you can see that the angle is very different because the water is more optically dense than the air. If you did not get this and you know your math is right, make sure you're in degree mode. That will make a difference. Okay? Okay, see you back in class.